When we delve into the realm of physics, particularly the study of forces and motion, we encounter some fundamental concepts that are crucial for understanding how objects interact in our world. One of the essential tools in this exploration is the free body diagram, a visual representation that allows us to see all the forces acting on an object. This diagram is not merely a collection of arrows on a piece of paper. It is a powerful tool that encapsulates the essence of dynamics and helps us analyze the motion of objects in a clear and systematic way. So, what exactly is a free body diagram? At its core, it is a simplified representation of an object, often depicted as a box or a dot, with arrows drawn to represent the forces acting upon it. Each arrow indicates the direction and magnitude of a force. For instance, if we have a box resting on a table, we might draw an arrow pointing downwards to represent the force of gravity acting on the box, and an arrow pointing upwards to represent the normal force exerted by the table. By examining these forces, we can begin to understand how they interact and how they affect the motion of the object. The importance of these diagrams lies in their ability to illustrate the concept of resultant forces. The resultant force, often referred to as the net force, is the overall force acting on an object when all individual forces are combined. To determine the resultant force, we simply vectorially add all the forces acting on the object. This means that we consider both the magnitude and direction of each force. If the forces are in the same direction, we add their magnitudes together. Conversely, if they are in opposite directions, we subtract the smaller force from the larger one, taking care to retain the direction of the larger force. Let's consider a practical example to clarify this concept. Imagine a scenario where two people are pushing a car from opposite sides. Person A pushes with a force of 200 newtons to the right, while person B pushes with a force of 150 newtons to the left. To find the resultant force acting on the car, we subtract the force exerted by person B from the force exerted by person A. This gives us a resultant force of 50 newtons to the right. The car, therefore, experiences a net force in the direction of person A's push, which will influence its motion. Now, why is understanding the resultant force so vital? The resultant force determines how an object will move. According to Newton's second law of motion, the acceleration of an object is directly proportional to the resultant force acting on it and inversely proportional to its mass. This means that if there is a resultant force acting on an object, it will accelerate in the direction of that force. If the resultant force is zero, the object will either remain at rest or continue to move at a constant velocity. This principle is foundational in predicting the behavior of objects under various force conditions. Furthermore, we must consider the relationship between forces and work done. Work is defined as the transfer of energy that occurs when an object is moved over a distance by an external force. For work to be done, two conditions must be met. There must be a force acting on the object, and the object must move in the direction of that force. The equation for work done is straightforward. It is the product of the force applied and the distance moved in the direction of that force. Mathematically, we express this as W e's Fxd, where δ represents work, F is the force, and d is the distance. Let's apply this to our earlier example with the car. If the resultant force of 50 newtons acts on the car and it moves 10 meters to the right, we can calculate the work done on the car. Using the work formula, we multiply the resultant force, 50 newtons, by the distance moved, 10 meters, resulting in a total of 500 joules of work done on the car. This work done translates into energy, which contributes to the car's motion, allowing it to accelerate as it moves. The concept of work done is crucial in various applications, from engineering to everyday life. For instance, when you push a shopping cart, you are exerting a force that moves the cart over a distance. The work you do is what allows the cart to roll forward. In contrast, if you push against a wall and it does not move, no work is done, despite the effort you exert. This distinction emphasizes the importance of movement in the definition of work. In summary, Free body diagrams serve as a foundational tool in physics, illustrating the forces acting on an object and enabling us to calculate the resultant force. This resultant force is the key to understanding how objects will move in response to the forces applied to them. Furthermore, when a resultant force causes an object to move, work is done and energy is transferred. These concepts are interwoven and form the basis of classical mechanics, allowing us to analyze and predict the behavior of objects in motion. Understanding these principles not only enriches our comprehension of the physical world, but also enhances our ability to apply this knowledge in practical situations, from designing safe structures to optimizing the performance of vehicles. The beauty of physics lies in its ability to connect these ideas, revealing the intricate dance of forces that governs our universe.